Assalamu alaikum. Welcome to the next lecture. This lecture will be the continuation of the previous lecture, that is the different features of the electrical appliances or equipments. So I'm again here discussing about the induction heater. In the previous lecture, I haven't mentioned the power factor. In that case, here I mentioned the power factor, and here P that is given over here is 2000 watt, and the rated voltage is 220 to 240, and I'm using this 220 volt just to calculate the worst case condition, and power factor I will be taking as 0.9, so it comes out to be 10.1 amperes. Now mixer and grinder. So this is the nameplate rating of mixer and grinder that I had. So in this case you can see the power rating is 700 watts, and voltage is 230 volt. That is what I have written over. Power is 700 watts and voltage is 230 volt. Since mixer and grinder, in both the cases we use a motor, that is electrical motor, and we know that for electrical motor we have to this divide by power factor as well as efficiency, and I have taken a rough value for power factor and efficiency to be equal to 0.8. It comes out to be 4.75 amperes. Similarly for incandescent lamps, so in incandescent lamps I have discussed it in the very first chapter. So how their currents are calculated. Usually the power rating is given, voltage rating is given, power rating is given, and the current will be given by W by V. So this is actually a more we can say extra information regarding this incandescent lamps. Nowadays we don't use incandescent lamps because of their higher power consumption, and most of the power that they consume is dissipated in terms of heat. Now what is this extra information? That 150 volt 100 watt bulb that draws a current of 0.67 amperes, it is calculated by using this formula. It will glow brighter than 220 volt 100 watt bulb, which is driving a current of 0.455 amperes at any voltage. For example, if the voltage is, because our voltage in our homes in practice varies from 80 volts to around 150 180 volts at the maximum, and this is the rating, it means that this bulb will consume 100 watt of power when a 150 volt voltage is given. Similarly, this bulb consumes 100 watt of power when 220 volt voltage is given to this, but when less voltage is given to it, it will consume less power depending upon the voltage. Similarly, for example, if the voltage is 150 volt to the supply and we first test this bulb, it will definitely consume 100 watt bulb and its glow is as per the 100 watt. And when the 150 is given to this bulb, so its wattage will not be 100 watt, it will definitely be very less, as less than this 100 watts. That's why I told you that this will glow brighter as compared to this. And usually when the voltage is low in our homes, we tend to use, actually in earlier days, now all these incandescent lamps are replaced by LEDs or CFLs, nowadays LEDs. So in the earlier days we usually replace these bulbs, and in common language we call them a voltage lamp. Even if it's a misnomer, but we usually recognize these type of lamps where the voltage rating is less and power rating is high. We call them as voltage lamp. It gives a brighter glow at lower values of voltage. Sometimes we might have 110 volt 100 watt bulb that will also glow brighter than these two. So in that case, that bulb is used when the voltage is very low as compared to 220 and 150 volt. One more extra information regarding this, I have perhaps told you earlier in the very first chapter, that if the two bulbs of the same voltage rating, are there, and the bulb having the higher power rating will glow brighter when they are connected in parallel, but the bulb having the lower power rating will glow brighter when connected in series. So this we have discussed as per we actually calculated their resistances and see what will be their power rating and how much current they will draw. So as per that knowledge, or as per that analysis, you will see that when the bulbs are connected in parallel for the same voltage rating, if they are having the same voltage rating, the bulb that has the higher power rating will glow brighter, and when they are connected in series, the bulb having the lower power rating will glow brighter. Now after that we have isolation transformer. Isolation transformer means when we have a transformer having two windings, two separate windings which are coupled through the magnetic field. So they are not electrically, they are not connected, they are magnetically connected. That's why they are not they are known as isolation transformer. The transformer that we have at our home is known as auto transformer or non-isolation transformer. That's actually a one single winding transformer. So in that case, there is no electrical isolation from primary and secondary. So what are the different ratings that an isolation transformer have? That is the voltage rating, that is the input or primary voltage and output voltage or secondary voltage. Its kVA rating. Usually you will see the transformer is not rated in terms of power, it is rated in terms of kVA or apparent power, which is denoted by the S. This is the apparent power, and frequency usually here the 50 hertz. So when you calculate the primary current, it will be this apparent power divided by the V1, which is the primary voltage. Similarly, secondary current will be the same apparent power divided by the voltage V2, that is the secondary voltage. This is for a single phase transformer. For a three phase transformer, the voltage rating is given same as that of single phase, V1 by V2, but here it was the phase voltage, here it will be the line voltage. kVA rating will be given as here the single phase kVA rating, it will be three phase kVA rating. Frequency will be the same in both the cases. So here the primary current will be S divided by, that is apparent power divided by root 3 into V1, that is the line voltage of the primary, because you will see the three phase apparent power will be given by root 3 V1 I1, that is VL IL, both will be the line values, that is line current and line voltage. Similarly, secondary current will be the same apparent power divided by root 3 into the secondary voltage, but again these two will be the line values, that is this will be the line voltage in the, at the secondary, this will be line current at the secondary. This is for the isolation transformer. A single phase 5 kVA to 30 by 115 transformer is used in a factory. Find the currents in the primary and the secondary. It's very simple, but it is just to make you understand how these currents can be calculated. Its rating is given in 5 kV, not in, that is the apparent power, not in the real power. So I1 will be equal to S divided by V1. That is S is 5 kV, that's 5000 VA divided by 230. 230 is the primary voltage. This is 21.74. So similarly, we can calculate I2. I2 will be equal to S divided by V2. S is 5000, V2 is 115, and it will be 43.78. So generally, in case of a transformer, you will always see that whenever the which side, even if the side which has the higher voltage will have lower current, the side which has lower voltage will have higher current. You can see the secondary voltage is 115, the secondary current is 43.78. So here also you can see the primary voltage is 230, that is higher as compared to secondary voltage, but primary current will be less. It is because to make their multiplication equal to this 5000. Now for three phase case, a three phase 250 kVA 11 kV by 450 volt distribution transformer. This is actually a transformer that we use in our locality. We may have 100 kVA, we may have 63 kVA, we may have 250 kVA. Usually these are the ratings that we use in our locality. That's why I have used the same values over here. This is the 11 kV, it's primary voltage. This is the secondary voltage, but it is the line to line. Its phase voltage will be around 230 volt. So it is used in a locality. So we need to find out the primary currents, primary and the secondary current. So the primary current will be equal to this 250 kV, that's 250 into 1000, that is 250,000 divided by root 3 is from the formula, and V1 is 1100. This is the line voltage. So it comes out to be 13.12 amperes. I2 will be equal to same S, that is apparent power divided by root 3, V2 is 415 volt. It comes out to be 347.8 amperes. This is how we can calculate the current on the primary and secondary side of a distribution transformer that we use in the locality and from which we can get the power. Now one is the auto transformer or stabilizer. So in general, an auto transformer is a transformer which is used or which is made from a single winding transformer. So depending upon the tappings on the primary or the secondary side, its voltage can be varied. And one more thing that I haven't mentioned over here, actually that has not to be mentioned over here, but I will tell you for your general information. The isolation transformer can have any turn ratio for it to be economical. It can range from 1 to any value, but for auto transformer or stabilizer, its turn ratio should be close to 2. It should be zero point 0.5 to 1.5, or we can, sorry, not close to 2, it should be close to 1. It should vary only from its range should be zero point 0.5 to 1.5. That is why it is very economical when we use it. So what are the different ratings or different nameplate quantities that are given for auto transformer or stabilizer? So in case of general auto transformer, one more information point, that we change the voltage manually, so we call it as auto transformer. And stabilizer, we may have some closed loop control and it changes the voltage or it stabilizes the voltage on its own, or we can say automatically. So that is the only difference, but the ratings will be like same, that it has an input voltage range from V low to V high. Let us say in our case it may be 80 volt to 250 volt high voltage. So output voltage has to be constant V naught, usually the rated voltage, that will be 230 or 220 in some cases. So its kVA rating will be fixed as S, that is its apparent power, and frequency will be 50 hertz again, because all our equipments in India are rated or designed for 50 hertz. So I1 will be equal to S divided by VL. It can be VL or VH, but for worst case condition, it should be VL, because for VL it will give highest current. Similarly, I2, since V2 is or V0 is constant, this is actually V0 or V2 are same. I2 will be equal to S divided by V2. It will not change because of the stabilizer property. So a single phase 5 kV 100 to 230 kV 230 oblique 230 volt auto transformer is used for regulating the voltage. This should have been actually 250, because this high voltage is actually more than this normal voltage, because for it stabilizes the high voltage as well. So this is usually the range that we have in our normal auto transformer that we use in our homes. You can see if we have 100 volt and we change it to 230 volt, you will see the voltage ratio is 2.3. So this voltage ratio having this type of transformer is not economical that we use. So in that case, its cost will increase and it may increase some losses as well. So it is not usually economical, but since we don't know its actual property, we usually uh, buy it. So whether it is economical or not, we don't know. So in that case, we buy it. So we need to find out its currents. So I1 will be equal to S divided by VL. Again, I have used here VL to have the worst case condition current, because when I use 230 or 250, I will get current slightly less than this. For 250, you please try to correct it, it will be 250. So what I mean to say is, you calculate the currents like this. You can see primary current will always be greater because of its lower voltage as compared to secondary current. So you need to have the wires connected on the primary of this type of transformer of higher cross-sectional area. You can choose it from the table that I have given in our last class. So for 50 ampere, what type of cross-section of the current you have to choose. So I will repeat one more thing over here, that using this type of an auto transformer is not economical. Even if you have to use it for this kind of voltage range, you have to use a isolation transformer to be for the economy of the you can say a transformer. Otherwise, using auto transformer, it will not be economical. Now coming to another, that is washing machine that we use. And in case of washing machine, you will see that we have two motors, or we have two separate chambers. One is for washing and is for spin. So for spin wash motor, that is usually a bigger motor and whose power rating is 340 watt, and for spin its power rating is 150 watt. So calculating the current for both the cases separately first. So this is for the wash motor. So I is equal to P divided by V into power factor and efficiency, assuming this to be the same value that we have used. So its current comes out to be 2.42 amperes, and the current for spin motor comes out to be 1.1 ampere. So the power rating for the whole machine, because usually these two may not run all the time simultaneously. In most of the cases you will see that this will run, this will not be running, or this will not be running, but sometimes they will run both simultaneously. In both the cases, in that case you will see that the power rating will be the summation of these two, that's 490, and divided by this value, it comes out to 3.5 amperes, and it will be similarly simply the summation of these two currents. So this was about washing machine. Likewise, we have television. You can see it from here. The range of voltage for television is 100 volt to 240 volt, and its wattage is 33 watt. And for 220 volt, it will draw a current of 0.19 ampere, and for 30 it is 100 volt, it will draw 0.42 amperes. This is for the television. Now CFL or LED, you can see we have a 7 watt this LED, and its voltage range is 220 to 240, and its power factor is greater than 0.9. We'll take this power factor to be 0.9. So when we use it, we get the value of current to be 0.0036. You can 0.036. It's also given that rated current is 0.035. It is close to that we have calculated. Now the important this appliance is the inverter. It becomes our important part in our day-to-day life. So inverter actually has two parts. One is the inverter itself, that is electrically it's known as converter, but usually the commercial name or the usual name we call it as inverter, and it has a battery. We'll first discuss the inverter part, and after that we'll discuss the battery part. So voltage rating, usually it is given voltage rating to be 230 volt, and VA rating, I mean, consider one of the inverter whose VA rating is given as 1100 VA. That is actually apparent power. It is also given in apparent power, not real power or any other power. Frequency will always be 50 hertz. So its current will be this S by V, because S is equal to, that is apparent power, is equal to V into I. It's 1100 divided by 230. It comes out to 4.8 amperes. Please try to understand. It means at full load it will be only drawing 4.8 amperes maximum if the load is connected across the inverter in such a way so that it draws a current more than 4.8 amperes. It will show overload. In that case, it will not allow you to draw the load which is greater than 4.8 ampere, because it has some inherent protection installed which will not allow you to draw more than 4.8 amperes from it. So what are the different loads that can be taken by the inverter? Definitely we need to see, actually in practice we need to see what are the loads that are connected to the inverter, and when we calculate the currents that are drawn by those loads at the inverter voltage, that is usually rated volt 230, and we sum up that current should be less than 4.8 amperes, and in that case inverter will work quite uh, appropriately. So let us say if we have incandescent lamps, we know that incandescent lamp will draw one incandescent lamp for 230 volt. It will draw a current of 0.434 amperes for 230 volt, and in that case if we only install incandescent lamps across the inverter, we can only go for 11 such bulbs. So 11 such bulbs will suffice, will be good for this inverter to we can say to not to load them, not to overload it. If we use the 12 bulbs, it will be overloaded. Similarly, LEDs, that is 7 watt, and one 7 watt LED will be 0.036 amperes it will draw. And how many LEDs will it bear? It will bear 133 LEDs. So we can install 133 LEDs to have a full load on the inverter, and it will work quite efficiently in that. case. And how many televisions it will load? And in this case, we are only installing LEDs and no other load we are installing. This is just a hypothetical example. Similarly, for a television, so we know that a television draws 0.19 ampere for 230 volt. So in that case, uh, it will be able to give supply to the 25 televisions simultaneously. So it will work well. For a domestic water pump, there will be only one, because you will see domestic water pump will have a current of, perhaps I don't remember, but it will be less than 4.8 amperes, but it will not be two times. If we use two water pumps, that the current of the two water pumps will go beyond this. So one water pump will suffice and it will be able to load this, or we can say it will be able to give supply to the domestic water pump as well, this type of an inverter. Now you may be wondering that if we use such type of loads on an inverter, that how much time this inverter will last. So that will depend upon the battery. Let us say we'll cover that part in its time taken by the inverter to discharge fully. Assume a 12 volt 150 ampere hour, that is the capacity, actually charge capacity of a battery, is connected to it. That means the amount of time that inverter lasts will depend upon the capacity of the battery. This capacity is the ampere hour, and ampere hour is actually another unit of the charge. You can see when you multiply ampere, ampere is the charge per unit time, multiplied by hour is the time. So time and time will cancel out, is the charge. So the capacity of the battery is given in terms of charge. So 1 ampere hour, that is 1 ampere, that is charge divided by time into time. That is, for SI unit, we have to convert this hour into this seconds. That 1 hour will be equal to 3600 seconds. It comes out to be 3600 coulombs. So 1 ampere hour is 3600 coulombs. So the total charge capacity of this battery will be equal to 150 into 3600, that is 540000 coulomb. So total energy stored by the battery when fully charged will be, because energy will be this charge multiplied by voltage, that is equal to charge multiplied by voltage, that is this 648,000 joules. Now let us say we are using it, we are fully loading the inverter, because in this case we can or you can use this type of approach to calculate the time for any load, but for the time being I am just calculating it for uh, full load. So 11 incandescent lamps that we are using for this type of inverter for fully loading it, so are connected as load. So the total power consumed by the lamps will be 11 into 100, that is 1100 watts. Let T be the time to discharge the battery completely by using this load. The total energy consumed by the load will be, so this will be, as we know, this is watt. When we convert it into energy, so watt into time will give energy, because watts are itself defined as energy per unit time. When we convert watts into energy, we have to multiply it by time. So the total time, the total energy consumed by the load will be equal to 100, 1100 into T. So the law of energy conservation says the total energy that is stored in the battery has to be supplied to the these bulbs, so as they will dissipate the, or they will convert it to light and heat energy. So that means 1100 T is equal to 648,000. So T will come out to be 5891 seconds, which comes out to 1.63 hours. You can see that if you fully load this inverter, it will only last for 1.63 hours. So in this case, it may slightly vary from, because it depends upon the, I have here used the approach of the linear approach, because this is linear characteristic of the battery, because sometimes the battery characteristics may not be linear, it will vary. It may be sometimes it may last for 2 hours, and it may sometimes last for less than 1.63 hours, so depending on that. But this is an ideal way of calculating the time, how time for a battery to discharge through this type of an inverter. You can use the same approach by calculating this time for any type of inverter or for any type of battery for different capacities. Now let's come to the electricity tariff. What do you mean by electricity tariff? It means nowadays we know that what is the tariff as far as mobile communication is concerned. Same type of tariff is used by the electricity company. We cannot see identical but same type of tariffs. So we'll first define it. It is the amount of money framed by the supplier for the supply of electrical energy to various types of consumers. That is known as electricity tariff. In the communication, or we can say in the mobile companies also frame the consumer for the supply of this, or we can say for the use of this their communication network. They will also charge you some money. In the same way, the electrical utility will charge the consumer the money for the use of electrical energy. So that type of money framed is known as the tariff. So you might have seen that the one type of tariff that is known as flat demand rate. I will discuss them in detail, but for the timing, I will just introduce it. What does this mean? In this case, a consumer is rated at a flat demand of 5.5 kilowatt. This is actually the rate that is uh, given by the PDD that is that's used nowadays. So we assume that a consumer has 5.5 kilowatt demand, maximum demand, and based on this maximum demand, that's maximum load, they will charge you 365 per month. So it is actually the tariff that is going on nowadays in villages and in towns and cities. They are having a tariff for load demand of 1 kilowatt hour, 1 kilowatt, and in that case, I think it is 967 or something else, but it is of the order of, it is similar in that, what I mean to say. And the second one is block meter rate. Here, the rate is dependent upon the demand, total demand. Here, the block meter rate, the rate is dependent upon the energy consumption. So energy consumption is usually measured in terms of units, and one unit is 1 kilowatt hour. We'll discuss that as also. So when this is done, then rupees 1.54 units, rupees 1.54 is charged per unit for first 500 units, 100 units, and rupees 2 per unit for other subsequent 100 units, and then 3.5 rupees 3.50 if the consumption is beyond 400 units. So in this case, in this way, this uh, tariff is defined. These are two types of tariff defined for electrical utility, and these two tariffs are also existing in our state. Now, what are the various electrical utility companies that are present in the JNK? The first one that belongs to the state itself is Jammu Kashmir State Power Development Corporation Limited. It is also known as JKSPDC. So actually, all the generation of the state that is owned by this company. And another one that is NHPC, National Hydropower Corporation. It is a private firm or semi-government firm or PSU firm. This also provides us electricity, and we also get electricity from the northern grid. So these three companies provide us the electricity that we are using in our day-to-day life. The above utilities supply the power to the state through Power Grid Corporation of India, that's PGCIL. These are actually transmission companies. So NHPC and Northern Grid, uh, they supply the power through the PGCL and also Sterlite Company STL. This also transmits the power from Northern Grid to the state. And state's own transmission system, that is Kashmir Power Transmission Corporation Limited, that is KPTCL. It also delivers power from within the state. It is governed or it is owned by the state itself. I think today I will stop over here. I will continue in the next class. Thank you.